Today we're lucky to be able to speak to Professor Tariq Munir, who specialises in energy engineering. He's the Professor of Energy Engineering at Napier University, and over the last 32 years he's published 210 papers and 5 books on the subject of solar energy and how to harness renewable energy effectively. He's also the driving force between Napier's PV facade, solar water heaters, wind turbines, solar sauna and hydrogen laboratory. Now, photovoltaics mostly use silicon as the semiconductor. Can you tell us a little bit about how that's made?
Silicon, as you rightly said, is used in the PV industry. That is the workhorse or the PV industry. It's also used in electronic industry and other industries such as steel production. Now let's take step by step. In the steel production, it will not be used in a very high purity, so 99.9% would be quite acceptable. Moving to the other extreme, in the electronic industry, the rule is 9 nines, meaning 99.99999 like that, 7 nines followed by the decimal point. That is a very high grade silicon. It's very expensive. Fortunately, it is not used in large quantities because it's used in a very small quantity in the integrated circuit chips. When it comes to PV production, it is 99 point followed by 5 nines. That much percent the purity has to be. So for that reason, the cost at the moment of the PV modules is fairly high. But the good news again, because of the economies of scale, the production costs are coming down all the time.
Right. That sounds like a really energy intensive process. I know the media like to use that as a way to make out that more energy is used in manufacturing a panel than ever is produced by one, but that's just simply not true at all, is it?
You're absolutely right. The energy payback period, as it is called, we have performed a very detailed analysis of the Napier facility. We found that despite the very low levels of solar energy in Scotland at such high northern latitudes, the payback period, energy payback period was about 8 years.
Right.
If you move southwards towards say mid-latitudes of England, the payback period will be much shortened. So it would be the order of maybe perhaps 6 years or so.
Right.
In Japan and other places, they have found the energy payback period is less than 5 years. And if you go to really sunny places, like between Tropic of Cancer and Capricorn, it would probably be about 3 years.
And can you talk us through the technicalities of the photovoltaic system here at Napier?
Sure. What we have is a facade which is covering basically 5 floors of a tall building. We have got 192 BP Saturn 90 watt modules, which were shipped from Madrid plant, and that is also a reason why the payback period is slightly higher than what it ought to be.
So you took that into your calculation?
Yes, the transportation costs were included. And these modules, they are arranging in 4 strings. Each string is connected to an inverter. At its peak, the design rated power is 16 kilowatt. But we will get that just for 1 or 2 days in the whole year. In the whole year, we keep an audit. We have kept an audit for the past 5 years. In a typical year, the module will produce something of the order of 10 megawatt hour of electricity. And they will also save something of the order of 7 tons of carbon dioxide.
The modules produce direct current, but we use alternating current. Can you tell us how that works?
You're right. The modules which are available currently on the market, they produce DC current. Although I must say immediately that there are now plans to produce larger modules with built-in inverters, so they'll give you straight AC current. They will be in the market within 2 years. But yes, the present modules, what we have to do is, we have to boost up the voltage. So presently at Napier, for example, we join the modules in rows, we boost up the voltage to 380 volts, so that there are minimum what is known as I square R losses. So there is very less energy lost by means of resistance because of high voltage. So we take this cable, which is a shielded cable. The cable travels some roughly about 30-40 feet. And then we have, on the F floor of our building, we have 4 inverters. The 2 bigger inverters, they can handle 6 kilowatt each. Then there are 2 smaller inverters, they can handle 2 kilowatt each. They are produced by Fronier, a French company, and we've also evaluated their efficiency and found them to behave in the manner they have been described. So their efficiency is over 96% to convert DC to AC current. Once the AC current is produced, it goes into the university grid and the energy is used up.
Right. And did you encounter any difficulties? Was there any problems when you were installing the panels?
The panels installation went like absolute magic. We had the cranes here on the side and cherry picker and all other equipment. And within 10 days, all the 192 modules were installed.
Right.
Yes. And then we had a certification from Scottish Power.
Right. And was there any restrictions through planning or through funders on the angle or the aspect of the panels at all?
Well, this part of Edinburgh is at the edge of Green Hill area, and that's a conservation area. So when initially we went to the city council, they said it will be unlikely that we'll get planning approval. But subsequently, when we made representations and they saw the potential for such a good demonstration project, the city agreed. The only problem we had was there were two bodies we were dealing with. The sponsors of this project, the Energy Saving Trust, they were demanding that the panels should be at an angle of 60 degrees, whereas the council was demanding that they should be flush with the wall, and hence they should be at a 90-degree angle from the horizontal. So we were caught between two agencies. In the end, as a compromise, both parties agreed for a 75-degree angle. So that's what they are at the moment.
And would there have been a better angle, and would it have made a difference to the energy output?
Sure. With the present angle, we are producing roughly 11 megawatt hour per year. That's the design value. If the angle was set at 40 degrees, which was what I was proposing, we would have got an energy output of roughly 14 megawatt hour.
Right, so a lot more.
So the payback period would have been considerably less also.
And what's the highest power it's generated to date?
So far, we have recorded a peak power of 13.7 kilowatt on a sunny day in May, if I remember correctly.
Right. And how does the output, how does it compare with grid electricity in terms of the emissions of carbon dioxide, say, per kilowatt hour?
It's very much in favor of PV. Taking into account all the embodied energy and all the shipping costs from Madrid and so on, we have calculated the payback, the carbon emission figure to be 44 gram of carbon dioxide per kilowatt hour. Compared to the grid network in UK, that figure is around 550 gram CO2 per kilowatt hour.
So it's less than a tenth.
It's roughly down by a factor of 12.
Right.
Yes.
Right. And how much did the installation cost?
The cost, you're right, is a difficult area at the moment. The total cost for this project was, because we were installing a very old wall whose structural integrity was in question. So we had to put some special structural supports.
Right.
So that boosted up the cost. The cost came to £155,000 for roughly 160 meter square gross area of the panels. And hence the payback period when they were installed 5 years ago was about 90 years.
Right.
Since then, the cost of electricity gone up by 50%. And now, with the feed-in tariff, the payback period will drop to under 20, perhaps 15 years or so.
Yeah, definitely. So in a way, it could be an investment, a way of people protecting their future, these technologies.
Sure. As I said, this is not a good example because of the very old wall we were dealing with. People installing this on the roofs, they will not have the structural elements put in place.
That's true.
So the payback period would be perhaps under 10 years.
Thank you very much for your time.
You're very welcome.